Time to get started. We're going to start something completely new, relativity. One reminder that I gave yesterday, one that is a reminder from the first day of this semester. I did get approval for us to do that field trip that's April 21. I will probably on Monday pass out some papers for you to put information on them. This is going to the Nebraska Academy of Sciences, which I'm guessing some of you have done. It is a scholarly conference, but it's a scholarly conference that is designed for collegiate and under. So you have a lot of presentations that are given by students like you who are juniors or seniors in college. A few years ago, we had a guy who was a freshman physics major give a presentation, which I was really impressed that they would do that. But it gives you a chance to, number one, see how scientists communicate, and number two, learn some interesting things. And so you'll have requirements of basically writing a very, very, very brief report on 4 talks and on 2 of the posters. Ideally, the field trip would come before the poster is due, so you could use what you learned from other people's posters, what didn't work for you and what did on your own. But like I said, the printer can only take them at such a time, so don't have that ability. So just to make sure those are on your calendars and you don't get surprised. Yes.
Do you know what time the conference starts?
Yes, the conference is actually an all-day conference, but you could do what you need to do in an hour to an hour and a half. So it starts at 8 and ends, I think, at 3, and you kind of just need to choose a time that you can be there for. Plan on at least 2 hours just to make sure you get everything done. So it's pretty flexible. One of the things that I was told was, well, I have permission to go to the conference, which is 5 miles down 48th Street. I don't have permission to provide any kind of transportation. So we will have to have students teaming up and, going together and arranging. And of course, I will be going, so I can provide some transportation as well. Did you have a question, Aaron?
I'm just wondering, so physics class will be canceled?
There will not be physics class that right. If you look in the schedule, it's scheduled to not have class that day. No, you have to go to a field trip and come back from my class. That's a good question, Mahala.
What's the lab posted for? Is that for our group project?
That's the group project, yes. All right. So the exam that's a week from yesterday will be covering the material through what we covered in class yesterday. So today's homework, the homework that's going to be assigned after class today and due on Friday, will cover what I lectured on in the lab, as well as maybe one question from this section of relativity. Usually there's not many questions I can ask from today's lecture and homework anyway. So let's get started with relativity. Here's my goals for today: reference frames, Galilean relativity, and the postulates of relativity. If we actually get to time dilation, well, then there's a few problems I can actually assign. So first, reference frames. The idea of a reference frame is so simple, it seems ridiculous to spend time on it, but relativity is all about reference frames. So if you don't start with reference frame, you've wasted the whole thing. So a reference frame is, as the words imply, the frame of space and time within which you make a measurement. So my reference frame right now is, I'm in this classroom, I see the classroom is stationary, and I see each one of you is roughly stationary. But if I walk, then with the reference frame of the classroom, I now have a velocity that's going to the back. Now I'm turning around just so the recording hears the words. Now I'm going forward in the classroom reference frame. In my personal reference frame, I'm stationary, and that screen is coming toward me. Right? That's if I take a reference frame where I say, I'm stationary, even though I'm walking with respect to the classroom, then I say, well, with respect to me, that was moving toward me. Now, I saw at least one person squint on that. I was saying, well, why would you do that? I assume that's why they were squinting. Well, think about when you are in an airplane. When you're in an airplane and you're sitting there, watching a movie on your iPad or talking to the person sitting next to you, do you feel like you're moving at hundreds of miles an hour? No, your reference frame is inside of that airplane. And you say, this airplane, I'm considering stationary. If I want to go to the lavatory, I'm going to get up and I'm going to ambulate, I'm going to walk, either to the front or the rear, and I would measure the speed I'm traveling, not as the speed of the airplane plus me, but just the speed I'm moving with respect to the airplane. So in that case, the reference frame is inside of a moving object. And the key to relativity is, how do we relate a measurement made by somebody on Earth with somebody who's in the airplane? And we can go to Galilean relativity, which was really simple. Galilean relativity is probably the relativity that up until today you have always espoused. That is, I think I have a question here. Suppose two people walk hand in hand on a moving sidewalk in an airport. They might walk at 1.3 meters per second with respect to a reference frame attached to the moving sidewalk, and 2.4 meters per second with respect to the reference frame attached to the building. Right? Different speeds for different reference frames. How fast is the moving sidewalk going in this problem? Does it say moving sidewalk? Yeah. And we had an answer that was how much? So 1.1 meters per second. Now for relativity, we need to understand how you made that so we can compare a different way of doing it. So how did you come up with that answer, Jonathan?
Just subtracted 1.3 from 2.4.
Okay, subtracted the two. So he said, and I'm going to use subscripts now, I'm going to say speed of the person with respect to the sidewalk is equal to 1.3 meters per second, and the speed of the person with respect to the earth was 2.4 meters per second. And so putting these together, he said the speed of the sidewalk with respect to the earth is equal to the speed of the person with respect to the earth minus the speed of the person with respect to the sidewalk. Now, he didn't write these equations down. He didn't do anything really complicated, but he just logically looked at it and said, well, that's got to be what it is. Now, to give you a standard for how to determine the speed of one thing with respect to another, notice I have these subscripts. The first subscript is the object, and the second subscript, I hit the blue button, is the reference frame. So, excuse me. Speed of the sidewalk with respect to the earth is VSE. So the way we usually do this is we say speed of the sidewalk with respect to the earth is equal to the speed of the sidewalk with respect to something plus the speed of that same something with respect to earth. So you see these two things are the first and the last. I did plus instead of minus. Now I have to think. I hate it when I think. No, I did mean to put it like this. The thing that goes in the middle is going to be the same thing for both. So in this case, it would be P and P. And so if we look at these, this one here is the same as what we had there. And then this one here has the opposite sign. Why the opposite sign? Because the indices are reversed. The speed of the sidewalk with respect to the person is the same magnitude but the opposite direction as the speed of the person with respect to the sidewalk. And so this here, VSP, is equal to minus VPS. And so you see the equation that we were given, well, that was implied, not directly given, by Jonathan, is this relationship. I put it this way because it's easy to keep track of your indices. The outer indices are the two that you're looking for the answer, and the inner index has to be the same thing. So this is actually what we use for Galilean relativity. And most people never consider that relativity. But that's saying, how do we relate the measurements in one reference frame to the measurements in another reference frame? And so the way Galilei devised is what we just did there, and it wasn't really crazy. Now, what we're going to be studying this week, probably next week, is called special relativity. And when I was your age taking this class and the teacher said we're studying special relativity, I thought to myself, that means we're studying the hard part. Why doesn't he start with the easy part and then move to the hard part? That's not what special means. Special is special because it's the easy part. So we're starting with the easy part, the special relativity. And what that term special really is telling us is that we're only talking about the relativity in inertial reference frames. So we have a new word here, an inertial reference frame. So we know the law of inertia. Katie, what's the law of inertia?
What is in motion stays in motion.
Right. An object in motion stays in motion unless acted on by an external object. And so an inertial reference frame is a reference frame in which that law is true. Now, when we started physics, I just gave Newton's 3 laws. I didn't say, oh, these are sometimes true. But now we're saying a reference frame where that's true is called an inertial reference frame. What's the difference in an inertial reference frame and any other reference frame, which we would call non-inertial? A non-inertial reference frame is a reference frame that's accelerating. If you have an acceleration, remember Newton's second law, the acceleration of an object is the net force of the object divided by its mass. If you have your reference frame itself is accelerating, like you're in the car and you're leaving the stoplight, the speed is changing, then if you consider yourself stationary in the car, you're still being pushed back into the seat as the car accelerates forward. And so we say, aha, you had an acceleration, you had a force and no acceleration in that case, because you're being pushed by the seat, but in that reference frame you weren't accelerating. But the reference frame itself was accelerating. So that's how we differentiate an inertial reference frame from non-inertial. And everything we're going to be doing here in special relativity is making measurements and calculations from within an inertial reference frame. Now, the surface of the Earth. Is the surface of the Earth accelerating? Okay, we have people shaking their heads both ways, and it's understandable. We tend to think that the Earth's surface is stationary. But in fact, the Earth is rotating. We do one rotation every 23 hours, 56 minutes, and 4 seconds? So we're rotating. We're also orbiting around the sun. We do one complete orbit around the sun every 365.2422 days. And the sun itself is not stationary. The sun is orbiting the galactic center. It takes millions of years for it to do that orbit, but we have all of this acceleration because changing direction is accelerating. But those accelerations are small, so to a good approximation, we'll treat the surface of the Earth as an inertial reference frame. So unless there's a question that is actually delving into something in particular, like, is the Earth reference frame truly inertial? Consider it inertial. Right? So don't take a problem and say, well, I can't do this problem because the Earth is, actually accelerating. We're going to do things within the approximation that it's an inertial reference frame. So here's an example of a non-inertial reference frame. If you're on a merry-go-round, you generally consider yourself stationary, right? I'm standing here and I'm not moving. But of course you're going around a circle. And so if you throw a ball, if you watch that ball after you throw it, it's going to appear to curve. That appearance of curving is because you yourself are moving. I have to admit, when I was in graduate school, we had a little rotating seesaw thing that we used for this demonstration in class. And after lab, some of my students and I decided to have some fun with it, so we're going as fast as we can. and the thing slid over. Fortunately, I leaned forward, but the seesaw took out the table leg on one of the tables. It would have been very devastating if my back would have hit it. So if you're on that merry-go-round, it's a non-inertial reference frame. And of course, you know as it speeds up, you get pushed really hard into the back. What's really happening when you get pushed very hard into the back of that merry-go-round? Yeah, you're trying to go straight because Newton's first law says you should go straight unless there's a force acting on you. And the merry-go-round is pushing you to change your direction. So if you were outside of the merry-go-round, you watch the person throw the ball, you would just see it travel in a straight line. No, I mean, vertical would not be straight, but the horizontal would be. So the same motion viewed from two different reference frames looks different. Which one of these reference frames is the one we're working in for special relativity? The inertial one, this one. So this here is valid, but the inertial reference frame is the one our equations will give us the answer for. One thing that we should always keep in mind is every reference frame is a valid frame. The person who is on the merry-go-round can make measurements of the force acting on them. It's a valid measurement, right? They're not going to have the wrong measurement because they're in that frame, but it's in a different reference frame, so it's different than what you would measure potentially in a different reference frame. So our first question, which of the following is an inertial reference frame? Answer all of them that are correct. So it's not just a single answer, it's all that are correct. I think Gila was the last one last time. She's going to be one of the last three this time. She can prepare us. Paris, Gila, and Nate. One of those three. And you're not going to be last, Gila. All right, everyone's answered. We have 14 that said a stationary car, 18 that said a car traveling at constant velocity, 3 that said a car accelerating along a straight road, and 9 said a car going around a curve at constant speed. So I'm just going to go through each one and have a person explain if it's a yay or nay and why. So Gila, top one, a stationary car, is that inertial? You said yes, and why?
Because it's not changing, or it's staying put.
Okay, because it's staying put. If you have zero velocity for your reference frame, then that's going to be non-accelerating. Okay, next up is Paris. A car traveling at constant velocity, is that going to be inertial?
Yes,
Why?
because even though it's moving, it's not accelerating.
Perfect. That's the hardest one for people to get, even though we had the biggest group here that was correct on it. Inertial doesn't mean stationary, it means not accelerating. So it has a constant velocity, not accelerating. Perfect. Okay, answer number 3, Nate. A car accelerating around a straight road, or along a straight road. I didn't hear if you said yes or no.
It's not.
Not. And what's the reason?
It's accelerating.
Okay, because it's accelerating. It's just that simple. It's accelerating. And then the final one, starting over on round 3, final one goes to Jordan. For a car going around a curve at constant speed, yes or no?
It's accelerating to no,
Okay, it's accelerating. Explain why it's accelerating.
because it's changing direction and velocity.
Changing the direction and the velocity means that it's changing velocity, so it's accelerating. So the correct answers here were these two were inertial reference frames. So making a measurement from one of those two will be a measurement that we can use with our special relativity. Okay, now we have some postulates of relativity that we're going to come up to This here is just laying out that we're going to consider the surface of the Earth an inertial reference frame, something I've already talked about. Not really true. If the Earth was, not inertial, we wouldn't have things like our hurricanes. Yeah, I've already covered this. I have two questions here. The first one seems silly, but it sets up the second one. I'm going to do this procedure twice with one that seems silly, setting up the second one. So a bus is traveling at 20 meters per second, and a student walks toward the front of the bus at 2 meters per second. And this is just a simple question. Is the student going to go faster than 20 plus 2, equal to 20 plus 2, or slower than 20 plus 2? Okay, this was apparently not as silly as I thought. So we have a range of answers here. Let's see what Mahala has to say about this. What did you answer and what was your reasoning?
I misread the question, but I would have put B just because I was going to add 20 and 2 meters per second.
Okay. And that is exactly what Galilean relativity said we should do, because we have the speed of the bus with respect to the Earth is 20 meters per second, and the speed of the person with respect to the bus is equal to 2 meters per second. And so the speed of the person with respect to the Earth is, what should my two subscripts be for the first one? Should start with P, because that's what the first one is here, blank plus speed of blank, and what should the second subscript be for the second one? E, because it's the second. And then the thing in between has to be the same. Well, that'd be bus. And so person with respect to the bus was 2 meters per second. Bus with respect to the Earth was 20 meters per second. And we got 22 meters per second, just like Mahala said. Now, the next question. A spaceship is traveling at 0.80 c. C, remember, is the speed of light in vacuum relative to the Earth, and fires a torpedo forward at 0.40 c relative to the speed of the spaceship. So we have the speed of the spaceship with respect to Earth is equal to 0.80 c. The speed of the torpedo with respect to the spaceship, 0.40 c. And we're asked for the speed of the torpedo with respect to the Earth. Okay, we had 6 that said slower and 14 that said 1.2 c, and nobody that said faster than 1.2 c. So, Jonathan Meckel, he is reading Einstein's book on relativity right now, so let's see if that has helped him here.
Well, okay. I actually was being a stickler and said A because technically it would, because you're applying a force on the torpedo, then the spaceship would have to slow down as soon as it fired it, so it would be slower than 1.2 c. But if you said that the spaceship is always 0.8 c, then you'd say 1% B would be fine.
Well, the fact is, your answer that you thought was just for being a stickler is the correct answer, but not for being a stickler. Because if that torpedo is going 1.2 c, that introduces a bit of a problem. Because we have a little rule that says nothing can go faster than the speed of light c. But this is exactly what you would have gotten using Galilean relativity would have had that 1.2 c. And so Galilean relativity fails. Now, this means we have to talk a little bit about light. People have been measuring the speed of light for a very long time. Some of the early measurements were wildly wrong. The earliest one, I can't remember the name of the person who did it. I trust that it's not on the next slide. I just forgot since last night. The earliest person to do it got up to the top of a mountain and had his assistant get to the top of another mountain, and each was holding a lantern. He said, okay, here's what I'm going to do. I have a shutter on my lantern. I'm going to remove the shutter. And as soon as you see the light, you remove your shutter. And I'm going to have a timer, and I'm going to time how long it is from when I remove my shutter to when I see that you removed your shutter. And then by taking the distance between two mountaintops and dividing by the time, of course you have to say it went twice, so 2 times the distance between them. Dividing by the time he measured, you get the speed of light. And so they did the experiment. And fortunately, this person was wise enough to not, well, this is before he published anything, but not proclaim a wildly incorrect answer. He realized there was no difference in the time that I would have had if I would have just been standing right next to him and I opened mine and he opened his and then I stopped the timer. The timer, of course, would probably be a sundial, or not sundial, but a sand, timer. This is an ancient Greek. So he said simply, it's faster than we can measure. Our reflexes were too slow to actually be able to measure the speed. There are other really awesome measurements that were made. One measurement, I think it was Remmer, something like that. He measured the orbit of a moon around Jupiter. I think it was, I don't remember which moon. But he measured the orbit of a moon around Jupiter and noticed that the period changed over time. And depending on where Jupiter was in its orbit, and based on that, he calculated the speed of light. Got a number at least, but one that was off by about 30%. And then over time, methods have improved. So today we have some really accurate methods of measuring the speed of light. But somewhere in the middle, we had James Clerk Maxwell, who, with his Maxwell's equations, remember just those 4 equations, calculated that there should be an electromagnetic wave, and that electromagnetic wave should have a speed that's 1 over the square root of the permeability of free space times the permittivity of free space. That's the result that James Clerk Maxwell came up with. Now, as we went further with the measurements, we get to Michelson and Morley, who really were looking for the medium of light, what light was traveling through. And so they were looking for properties of that medium, and they said, well, let's measure the speed this direction and measure the speed this direction. Because if it's something like air, if there's a breeze, we'll measure a different speed because it's being traveling in a moving medium. And no matter what they did, they never found that the direction they measured made a difference. And so they concluded that there was no medium for light to travel. That destroyed a whole theory. But as an outcome of this, well, flat earthers say, no, their experiment didn't say that at all. All their experiments showed is that the earth is stationary, that we're not rotating. That's what the flat earthers say, just so you know. They consider that one of the great experiments of proving that the earth is flat. One of the things that came out of this was if there's no medium, then the speed of light in vacuum should be the same everywhere. Vacuum meaning you have nothing to interfere with the light traveling. When you have something that's not vacuum like air molecules, the light comes and you'll have a little absorption and re-emission by the air molecules. But that absorption and re-emission slowed it down. If you have something with more densely packed molecules, like in glass, it's going to do that more and slow it down more. So that's why having light go through something other than vacuum is always slower, because of the process of being absorbed and re-emitted. So if the speed of light in vacuum is always the same, and any reference frame is valid, then Einstein made as a postulate of relativity that the speed of light in vacuum is the same in every inertial reference frame. So it doesn't matter what reference frame you're in, the speed of light is going to be the same. So I actually asked this question on an exam, I think last year in this class, and a lot of students missed it. So I'm going to tell you right now. The question was, somebody on Earth shoots a photon torpedo. What's a photon torpedo? It's a laser beam, okay? They shoot a photon torpedo that travels at the speed of light. And it flies by a rocket that's traveling at half the speed of light. How fast is that photon torpedo traveling with respect to the rocket? The speed of light. Like half the class said, oh, half the speed of light. That's what you get applying Galilean relativity, but that ignores this first postulate that says the speed of light in vacuum is a constant. Doesn't matter what reference frame you're in, it's still the same. Now that means that something has to give, that equation that we learned from Galileo, the one that was just inherently made sense, isn't right in all situations. We have to come up with another variation on it, and we will. I think this is hilarious. You'll probably just think I'm a stupid dork. When I was in graduate school, I went to a comedy club, and while the comedian is up there telling somewhat funny jokes, some random stranger I'd never met before, and I started talking about this problem right here. And our discussion got so animated, the comedian had to tell us to shut up. Now, Einstein talked about what would happen if you had a car that could fly at the speed of light. Right, so this is what we call a Gedanken experiment, a thought experiment. That's the only kind of experiment Einstein ever did. Right? He didn't do experiments like you're doing in lab, except for as required in school. Everything he did was based on thinking things through. Can you put the water away? We don't want it to have.
Oh, it's mine.
Yeah. The food or drink just. I know I haven't enforced it before, but now we're doing stuff with chemicals, so I don't want to have it. So if you have a car that's traveling at the speed of light, and you flip on the headlights, what do you see? Okay, so Jordan said light. But if you see light, is the light stationary or moving?
See, this light isn't stationary or moving.
Well, the light is moving. If I do something like move my hand here, I see the shadow, remove it, the light comes down, hits it, it's moving. Right, it's not stationary. If I went like this, it wouldn't cast a shadow if it was stationary. So, stationary, moving.
Moving.
Okay, moving. Now, if the light is moving, then that means that the car going the speed of light, somebody on Earth would say, well, light's not moving with respect to the car, because it's moving with respect to you. But the other side of the coin is if the person on Earth says that the light's staying right with the car, not moving, then the person on the car says it's not moving. He can come out there and say, yeah, here's the electric field here, here's the electric field here, and you would have a stationary electromagnetic wave, which isn't possible. And as you can see, you have a conundrum, two things that can't work together. Now, of course, we have the fact that no car can go the speed of light, but that doesn't change the fact that we have a problem. And so Einstein's conclusion that the speed of light in every reference frame is the same means that we have to have something else going on. And what's that something else? This is where I get to talk totally nerdy. The warping of the space-time continuum. Distances and times vary depending on your reference frame. Now, that's kind of odd. That means that it's possible for you to move from one reference frame to another reference frame and age at a different rate. So we'll be looking at later in this class period an example of people aging at different rates and a paradox that brings up. So here's the two postulates of relativity. The first one, the laws of physics are the same in all reference frames, in all inertial reference frames. All of the physics things we do are the same in every inertial reference frame. The second one, the speed of light in vacuum, is the same in all inertial reference frames. Just those two rules are what leads to all of the monkey business in special relativity. Let's get to The monkey business. Well, here's something. I can't do demonstrations of relativity for you in class. Right? Relativistic, for special relativity, you have to have relative speeds that are greater than 1/10 the speed of light to see a difference. I can't make anything except for light or electrons travel as fast as 1/10 the speed of light. So I can't do any demonstrations of relativity. And so this is where you have to actually have faith. You might remember like the first day or two of class, I said, you shouldn't take things on faith. The teacher said it, the book said it, and so I believe it. You want to think things through. And usually we try to have demonstrations to help you understand. But we can't do a demonstration here. We do have some examples that can be observed. You guys know what's happening the first day of school next year, right? We're having a solar eclipse. The moon is going to pass between the earth and the sun and block all of the sunlight. Here in where we are in Lincoln, it will be complete for, about a minute and a half, but we're right on the edge. It probably won't get super dark because if you look at the other side of Lincoln, there will actually be sun hitting over there, which means the sky won't be dark everywhere you look. If you just go a little bit south of here, like down to Beatrice, you'll be right in the middle, and it should be like darker than the middle of the night for 2.5 minutes down there. But when this happens, because it's dark, you're able to see stars that are close to the sun. And one of the things that can happen during a lunar eclipse is you can see the same star 2 different places. How does that work? What did I say happens with relativity? It's really nerdy. You warp the space-time continuum. Now we know that the starlight travels in a straight path. But if the space-time continuum is warped, that straight path doesn't look straight to us. And so the sun, general relativity says that mass also warps the space-time continuum. So the sun warps the space-time continuum such that light coming from the star will come and bend around the sun. So here's the sun. Here's a star, and its light goes in all directions. Gets warped around the sun, so you're down here on Earth. Red will do for me. You're down here on Earth, and you see the star both here and here because it warped around the sun and comes to you from different angles. Now, of course, you might say, how do I know it's the same star and not 2 different stars? Well, you can observe the sky and see that as the reference point moves so we can see what's there, there's only one star. You can also measure the spectrum of the light, that is the different colors present using a diffraction grating, and see that you have exactly the same spectrum. Every star has a slight variation. If it's exactly the same, it has to be the same star, just like thumbprints. So we have examples. Another thing that uses relativistic calculations is your GPS. I have my cell phone here that works as a GPS receiver. It's amazing. It can tell me where I am within, 25 feet or so. Sometimes better. How does that, do you know how that works? I'm going to go with one of the people in the UAV class because we had a lecture on that. Go ahead.
So, if I remember this right, the satellite sends out a signal. And as far as I remember, the signal has the time that it was sent out according to the point of view of the satellite, and so you need highly precise timekeeping on the satellite. And when it gets to your phone compares the time that the signal says it left the satellite with its internal clock and takes the difference to find the distance.
The action of the receiver you have a little bit off, but otherwise you're right. The satellite, all of the GPS satellites out there, we say we have a constellation of GPS satellites. And they're sending out a signal that goes back to when I was a child. We had a phone number we could call, what was it, 800 POC or something like that. And it would say, at the beep, the time will be 10:35 and 20 seconds. Beep. And it would just do that over and over. That's what the GPS satellites are doing. Except for they're saying, I'm Bob, and at the beep, the time will be 10:35 and 22.69, a whole long string of time. Very accurate. And so it identifies which satellite it is and what time it is. And if you have one satellite and you know the exact time, then you can calculate the distance to that satellite. If you have two satellites and you know the exact time, then you can calculate the distance from each of those satellites, and now you can restrict yourself to being somewhere on a circle. And then if you have a third satellite, you can restrict yourself to being one of 2 points, one above the surface of one above the elevation of the satellites and one below the elevation of the satellites. We can be pretty clear that we're below the elevation of satellites. And a fourth one would give you a single point. Now, the one thing that I said was not exactly correct. Your phone doesn't have to have exactly the right time because it takes the information from the different satellites, knowing their positions and getting the times, it actually calculates what the correct time is based on those times. So you don't have to have the right time in your clock because it will be calculated. But the key to all of this is you have to have a really accurate clock in that satellite. If the clock is not keeping correct time, you don't have correct locations. So they have to make clocks that will keep correct time when they're in the satellites. But those satellites aren't stationary, they're moving. Which means that we're warping the space-time continuum. Time can pass at a different rate. Likewise, you're farther away from the Earth's mass. The Earth is warping the space-time continuum. You have those two things that have to be corrected for. And so they calculate what rate the clock needs to keep time so it'll be correct when it's put in orbit. So the clocks don't keep correct time on Earth. But when they put them in orbit, then they keep correct time. So it's another example of how relativity works. So special relativity, in 1905, Einstein wrote a paper on that. I don't think I've talked about Einstein much in this class yet, right? This is the first time it's come up. So Einstein, much like Newton, kind of wasn't a great student because, just like you might not be interested in what I'm teaching. He was interested in what he wanted to learn, not in what the teachers were necessarily teaching. And so he did famous things like, how was Einstein in math? A lot of people think he was bad at math. He made statements about having big problems in math. Well, I would say that he was brilliant in math. He just didn't like math. So when he's in college, the university, he's taking high-level math classes. He doesn't like math. So what does he do? He does not attend class. But of course, you do have to attend for the tests. And so the night before a test, he'd get together with his buddy and say, okay, what do I need to know for this test? And in the night, his buddy would teach him what he needed for the test, and he had passed his classes. Can you find somebody bad at math that can do that? I don't think so. Now, why did he have such problems with math? Because he was trying to solve some problems in relativity that have never been solved still today. He was trying to solve enormously hard problems. So yeah, he was having terrible problems with math because he was trying to do stuff that's impossibly hard. Okay, so in 1905, he was working at the patent office as a clerk, loving life, because as a clerk at the patent office, he got to read all these patent applications and say, ooh, that's a great idea, or oh, that'll never work. And so he was just looking at ideas and he loved it. And he would read scientific papers, and from what I've read, him and his friends would get together at the pub, throw back some ginger ale, and laugh at mistakes people made. Then in 1905, he himself wrote 3 papers. 3 papers. In no particular order. Paper number 1 explained Brownian motion. You guys have all taken some biology, right? Okay, not all of you. Brownian motion was American scientist Robert Brown noticed that when he was looking at pollen grains in water, looking through the microscope, he saw the pollen grains moving. And he said, well, what's making those pollen grains moving? It must be, using his vernacular, cavorting beasties. Or in other words, he thought it was little submicroscopic light that was hitting it, making it move. And Einstein wrote a paper saying, no, that wasn't submicroscopic light. The water molecules are not stationary in still water. That seems wrong. Still water means stationary, right? They said, no, the molecules are moving around. We have the kinetic theory that says the molecules within the water are bouncing around everywhere. And so what he was seeing was the bouncing of water molecules off of the pollen, because the pollen was so light that the mass of the molecules could actually make it rebound. So that was one paper. The next paper will be on the photoelectric effect. Remember, I mentioned that Newton believed that light was a particle, but then Thomas Young showed with his double-slit diffraction that light had to be a wave. That's what we studied in lab yesterday. Well, in studying black body radiation, that is the light that comes from a lamp because it's hot. The light something gives off because it's hot. And trying to explain the shape of that curve, to the best of the physics knowledge, we had the work of Rayleigh and Jeans, that just didn't work. Regular standard classical physics predicted that no matter what the temperature of an object, it should be giving infinite amounts of energy off in the ultraviolet range. This was called the ultraviolet catastrophe. Right? It didn't make any sense. They knew that couldn't be right. Catastrophe was the catastrophe of the theory failing. So a researcher who was doing research on this sent off a telegram to Max Planck saying that at low temperatures it behaves like this. And Planck wrote a postcard back to him that night saying, well, if that's the case, then it must have this equation. And he wrote an equation that gave the right shape for the amount of radiation as a function of its wavelength. Now that was just based on fitting, just fitting the data. It wasn't based on physics theory. And of course, as a physicist, being able to get the right answer on the problem isn't what I'm grading, right? What is most of your grade based on? On concepts, understanding why, being able to explain why it happens. And so Planck had come up with, here's the answer, but he didn't have a reason for it. And so, you feel like a waste of space if you don't have a reason for it. So he sat down and tried to figure out, why is my equation correct? And a few months, like 9 months, 6, 9 months later, he published, okay, I figured it out. If light truly comes in packets of energy, with each packet having an energy proportional to the frequency, then I can give you a physics explanation for why my equation is correct. So he didn't actually believe that light came in packets, but he said, if it did, I could give you an explanation. And so Einstein's second paper, the one on the photoelectric effect, said, yeah, light really does come in packets, what we call photons. And that's what he got the Nobel Prize for. The third paper was on a theory of special relativity. And looking at the clock, we're not going to get into special relativity today. Like I said, we're not going to get there. But that was his third paper in the same year. And as you probably understand, that special relativity paper changed the world. But so did the photoelectric paper and the Brownian motion paper. In 1900, many physicists went on record as saying, we completely understand the world. We've got it down. There's really not much new to learn. And then 5 years later, Einstein writes these three papers, and they find out, yeah, we just were wrong in a lot of different areas. We have to take that into account even today. We feel that scientists must have it down. So I've been up here and I've been lecturing for a year and a half, semester and a half. Seems like a year and a half, doesn't it? I've been lecturing for a semester and a half on our understanding of physics. Somebody like Einstein could come around and show us, wow, a lot of those things were pretty naive. So we have to keep that in mind. That's one of the great things that Einstein showed the scientific world is, don't get complacent. You don't know everything. About 10 years later, he wrote a paper on general relativity on how mass affects things. We will end today by talking about the correspondence principle. The theory of special relativity is really a theory that applies when things are moving really fast. The stuff I've been teaching you so far works very, very, very well as long as the speed is less than about 1/10 the speed of light. The correspondence principle, that's a principle, right? It's not a hard, fast rule, but it's a pretty good one. says that when you come up with a new theory on how things work, it better explain the correct values in the region where the old theory is applicable. So what that means is special relativity had better give us the right answers at normal everyday speeds. We won't use it at normal everyday speeds because it's more complicated. Hence, we haven't used special relativity starting right out of the gate. We use Galilean relativity. But if we start going fast, the two diverge, and then we have to use the special relativity. So that's the correspondence principle here. And it's time for us to end the day. So we'll start with simultaneity and time dilation next class period.